Introduction. Measurement has been inseparable part of physics and other engineering disciplines. It is also used in commerce and in home and elsewhere, but these measurements are related to three fundamental quantities of mass, length, and time. The aim of this experiment is to measure length by using meter rule, vernier caliper, micrometer screw gauge, measure time using stopwatch, and we measure mass using beam balance. Requirements: meter ruler, vernier caliper, block pads, micrometer screw gauge, stopwatch, this is digital, stopwatch which is analog, test tube, beam balance, water, beam balance again, and blocks of wood. Hold a meter rule and observe the ends of that meter rule. Check if the zero mark is at the end. If it is not at the end, then take 1 centimeter mark and place one end of your wire at that mark and read .78 centimeter. Make sure that your eye is vertically above that mark which you are reading. You have to move 1 centimeter more. That is, instead of 78, you read at 79 centimeter mark. Then that will be your length. When using meter rule, you have to be careful because the meter rule is supposed to be starting at zero mark, but because of use, sometimes there is a worn out. So it is better if you find a point which is clearly readable, and after reading, you will subtract that value which you have added. Sometimes the length which we need to measure is small, such that by using a meter rule, the length will have a big error. For example, if we want to measure the width of this pad, by using a meter rule, you can't get the measurement clearly. So instead, we use another instrument which is more sensitive, and this is the vernier caliper. Before we use this vernier caliper, let us look at the features of the vernier caliper. Hold your vernier caliper. Observe the lower part where we have the jaws. Those are called the jaws, and these are used for measuring outer dimensions. Above it, we have other jaws. These are used for measuring inner dimension. Then, when you open your vernier caliper, there is a stem which is protruding out. This one is used to measure depth. The vernier caliper has two scales. We have the major scale and we have the vernier scale. Hold your vernier caliper and close the jaws of the vernier caliper and observe that the first mark on the vernier corresponds exactly with the zero on the main scale. If the two do not coincide, then there is a zero error. How to read the vernier caliper? This is the situation when the two jaws are closed. Zero mark on the main scale corresponds with the first mark on the vernier scale. Also, the last mark on the vernier scale corresponds with another line on the main scale. So in this case, no reading. 0 on linear scale corresponds with 0 on vernier. Place the pad between the jaws. Then read the width of that pad. If your vernier caliper showed this feature, then the first mark on the vernier is at this position, which is 1.4 centimeter. But this exceeds slightly. To get the part which has exceeded, we use the vernier to get the value. We count the divisions on the vernier which exactly corresponds with a line on the main scale. In this case, this is our situation. This is the division which coincides with the line on the main scale, and it is the fifth division on our vernier. This vernier is enlarged scale which divides the smallest part in our main scale, which is 1 millimeter, into 10 equal parts. So the fifth division represents 0.05 centimeter. Our reading will be the reading on the main scale, which is 1.4, plus the reading on the vernier, which is 0.05. Then the width of the pad is 1.45 centimeter. The vernier caliper is also used to measure the external diameter of a cylindrical object. In this case, we have a test tube. Open the jaws and place the test tube. Read the value on the scales. We will get the external diameter of the test tube. To get the internal diameter, we use the other jaws. You place the jaws inside the test tube and you open your caliper. You take the readings, and that one will be the internal diameter of the test tube. Use the vernier caliper to measure the depth of water in the test tube. As the jaws are opened, the stem protrudes outward, and the length of that stem is equal to the reading on the jaws. Then read your scales. You will get the depth of water inside the test tube. In measuring small lengths, such as a diameter of a wire, we use an instrument known as the micrometer screw gauge. Features of the micrometer screw gauge are shown on this diagram. We have the metal frame, we have the jaws, but in this, the jaw is known as anvil, which is the fixed one, and the movable one is spindle. We have a lock on this frame. We have two scales, the sleeve scale, which we call the main scale, and the timber scale, which is known as the vernier scale. This part which holds the scale is known as the timber, and another part which we use to rotate the micrometer screw gauge is known as the latchet knob. When closing the jaws, it is advisable to use the latchet knob to close, because after closing it will produce a crackling sound. But when you use the thimba, it can apply a large force and cause the object which you are measuring, if it is not stiff enough, to flatten. In measuring using the micrometer screw gauge, note the scale on the thimba. Some micrometers have the scale up to 50 divisions and others have 100 divisions. If we take the 50 division thimba scale, by rotating it once, this will just move half of a millimeter on the main scale. So half of a millimeter has been divided into 50 divisions. Therefore, each division on the thimba is 0.01 of a millimeter. When using the 100 division thimba scale, by rotating it once, it covers 1 millimeter. So that millimeter has been divided into 100 divisions, and each division is 0.01 of a millimeter. Before you use a micrometer screw gauge, close it and check if the zero on the circular scale corresponds with the line on the main scale. If that does not happen, it means your micrometer screw gauge had zero error. When closed and the scale is arranged this way, then no zero error. When closed and there are, say, 2 divisions above 0, the error in this case is positive, 0.02 millimeter, because we have 2 divisions above 0. And when closed and the mark is below 0, then we have the error of negative. We have 2 divisions here, so this is negative 0.02 millimeter. The zero error can be adjusted by turning the screw on the anvil, but if that is not possible, we use the cancellation. If the reading before 0 is positive, 0.02 millimeter, the final reading which will be obtained will be subtracted by this amount. When using the scale with negative error, the final reading obtained should be added with this value of 0.02 millimeter, or the error which will be indicated by the micrometer screw gauge. When the jaws are closed, the 0 on the vernier is at 0 on the main scale, and when you rotate it, the reading should be taken at the end where the thimba starts. In this case, the scale is reading 7 millimeter. When the micrometer screw gauge opens and gives this reading, the linear scale is showing 1.0 millimeter. The circular scale has 47 divisions. Multiply it by 0.01, we get 0.47 of a millimeter. So the total reading will be the sum of these 2 scales, which is 1.47 millimeter. In this situation, the micrometer has opened and the main scale is showing 7.0 divisions, while the circular scale is showing 22 divisions. So the sum of the length is 7.22 millimeter. In this case, the main scale is showing 8.5 millimeter. 5, 6, 7, 8 and a half. But the circular scale is showing 26 divisions, which correspond to 0.26 millimeter. So the total length is 8.76 millimeter. Measurement of mass. To measure mass, use the beam balance. The beam balance here has two scales. We have the scale which is showing 100 grams, one which shows the interval of 10 grams, and we have the dial which has the interval of 1 gram. Place a wooden block on the pad, adjust the circular scale, nothing happens. Move the 10 interval radar, nothing happens. Move the 100 interval radar, stick there. Move again the 10 gram interval. Adjust the circular scale until you get the balance. The mass of this block is the sum of the mass indicated here and mass indicated here and mass on this scale. So this is 200 plus 10 plus 3.5. The mass of the block is 213.5 grams. Note that before you use the scale, check if it has no zero error. For example, in this case, the line does not correspond with the 0. You can make the fine adjustment by moving the knob on this scale. Now when at rest, the mark corresponds with 0. So the balance is free of 0 error. We have another scale which only uses radars. We have 4 beams. 1, 2, 3, 4. So this is the 4 beam balance. Place the object whose mass is to be determined. Move the radars. So the balance is obtained. The mass of the block is the sum of the masses recorded by the radars. 200 gram plus 10 plus 4 plus 0.08. Therefore, the mass of the block is 214.08. Another type of balance is this one, where we have 2 pans. In measuring the mass of this, we have a set of masses. Measurement of time. We measure time using stopwatch or stop clocks. Stopwatches are of different kinds. The 2 major ones are the digital stopwatch and analog stopwatch. Digital stopwatch is easy to use. We have the two knobs. One is for starting and stopping, and the second one is for resetting. Analog stopwatch has different scales. In this case, we have the ordinary one, which is the scale also used by the stop clock, where we have a pointer showing the seconds and another one showing minutes. Another type is the 60-second revolution stopwatch. This black pointer indicates seconds, and once it indicates seconds, the minutes are indicated by the small clock inside it. The division here corresponds to the number of revolutions taken. Another scale is the 30-second revolution stopwatch. One revolution of this black pointer makes 30 seconds, and the second revolution makes up to 60 seconds. The small scale inside it is showing the number of minutes expired. A 6-second revolution stopwatch, it makes one revolution in 6 seconds. This one is more accurate than the former two stopwatches. And inside there is a scale which is indicating the minutes. For example, from 0 up to 1, we have 10 divisions, each division showing one revolution or 6 seconds. Conclusion. The basic quantities of mass, length, and time can easily be measured in the laboratory if we have the instruments indicated.
Some materials are insoluble in water. These include sand, iron fillings, and lead shots. The insolubility helps to find the air densities by using density bottle. The aim of this experiment is to find the density of sand. Requirements. We have density bottle of 50 mils or 50 centimeter cube. We have sand, water, beam balance, and masses. Precautions. Handle with care the density bottle because it breaks easily when dropped. By using beam balance, measure the density bottle with its stopper and record it as M1. We have masses here. This is 20 grams. This is 200 milligrams. Also this one is 200 milligrams. The mass is balanced with 20.4 grams. So M1 is equal to 20.4 grams. The mass of empty density bottle with its stopper is 20.4 grams. Add sand in the density bottle. insert the stopper and then measure the mass of dense bottle with sand and its stopper and record it as M2. Here we have 20 grams mass, another 20 grams. This is 2 grams. The mass is balanced with 42 grams. Therefore, M2 is equal to 42 grams. Add water in the dense bottle until it is full. Dry the outside of the dense bottle. Then measure the mass of dense bottle with sand and water on top of sand. Here we have masses. This is 50 grams. We have 20 grams. We have 10 grams. We have 2 grams. We have 500 milligrams, 200 milligrams, also 200 milligrams, 200 milligrams. The mass of dense bottle with sand and water and its stopper balanced with the mass of 83.3 grams. Pour out the content of the dense bottle. Clean the dense bottle. Dry the outside of the dense bottle. Fill the dense bottle with water. Insert the stopper until the water is raised up to the center of the central tube of the dense bottle. Then clean the dense bottle, the outside of the dense bottle, and measure again the mass of dense bottle with water. 20 grams. This is 50 grams. This is 500 milligrams. Okay, let us use 200 milligrams. And 100 milligrams. The mass is 70.3 grams. The mass balanced with 70.3 grams. Mass of sand will be equal to M2 minus M1, which is 42 minus 20.4 grams. This will be equals to 42 minus 20.4 21.6 grams. Mass of water added will be equals to M3 minus M2, which is 83.3 minus 42 grams. So mass added will be equal to 41.3 grams. Mass of water filled in the density bottle will be equal to M4 minus M1. This will be equal to 70.3 minus 20.4 grams. This will be equal to 49.9 grams. Mass of water displaced will be equal to M4 minus M1 minus M3 minus M2. M4 minus M1 is here, mass of water filled in the bottle, which is 49.9 gram, minus M3 minus M2, the mass of water added, which is 41.3 grams. Therefore, mass of water displaced will be equals to 49.9 minus 41.3. This will be equals to 8.6 gram. As we know that density of water is equal to 1 gram per centimeter cube. Therefore, the volume of water displaced will be equal to mass of water displaced, which is 8.6 gram, divided by density of water, which is 1 gram per centimeter cube. Therefore, the volume of water displaced will be equal to 8.6 centimeter cube. But the volume of water displaced is equal to the volume of sand. Is equal to volume of sand, which is equal to 8.6 centimeter cube. Find now the density of sand. Density of sand will be equal to mass of sand divided by volume of sand. This is 21.6 gram divided by 8.6 centimeter cube. Therefore, density of sand will be equal to 2.51 gram per centimeter cube. The density of sand is found by using density bottle, beam balance, and water. The source of errors may be insensitivity of beam balance. By using the same procedure, find the density of lead shots.
If a body is totally or partially immersed in a liquid, that liquid appears to increase in its volume. The increase of this volume is due to the weight of the body which is immersed in that liquid. The aim of this experiment is to find out the relationship between the upward force or upthrust and the weight of the fluid displaced. Requirements: water, beakers, thread, stone, Eureka can, spring balance, and retort stand. Measure the weight of an empty beaker. And record it as the weight 1. Which is equal to 55 gram force. Tie a stone with the thread as this one, it is already tied. Then put another beaker at the bottom of the spout of the Eureka can. Fill the Eureka can with water. Until water starts to flow through the spout of the Eureka can. Wait until the overflow water stops, or can say that until the final drop of the overflow water. Just wait. Then measure the weight of the stone in air by using a spring balance. Record the weight of the stone, and the weight should, let us call it weight 2. The weight is 65 grams force. Put the known weight beaker under the spout of the Eureka can and immerse the stone inside the Eureka can. Make sure it is totally immersed, but does not touch the base of the Eureka can. Wait for the water to overflow through the spout until the last drop. When the water is flowing, also the mass of the stone, when it is totally immersed in water, should be recorded, and this will be called the weight 3. Weight of the stone in water, call it weight 3, equals to 40 grams force. Take out the stone from water and measure the beaker with the water collected and record its weight as weight 4. Weight of the beaker with water, weight 4, equals to is 80 grams force. Find the weight of water displaced, whereby after collecting the data, find the weight of water displaced, which will be weight 4 minus, we subtract weight 1. This will be equal to 80 grams force minus 55 grams force. It will be equal to 25 grams force. Then after, find the apparent loss in weight. Which is equal to weight 2, weight of a stone in air, minus weight 3, which is the weight of a stone when it is measured in water. It will be equal to 65 grams force, subtract 40 grams force. The answer is 25 grams force. From there, we can conclude that the apparent loss in weight is equal to the weight of water displaced, and also the upward force, which is upthrust, is equal to the weight of water displaced.
When a rubber band is stretched and released, or a spring is compressed and released, they do resume their original shape and lengths. The ability of a material to return to its original shape and lengths is known as elasticity. The aim of the experiment is to find out about the relationship between extension of a material and the load applied. Requirement: a spiral spring, a pointer, masses, a meter rule, piece of wood, and 2 retort stands. Procedure: clamp the meter rule vertically on the retort stand with a 0 mark on top as shown in the diagram. Suspend a spiral spring on the clamp on the second little stand. Below it, attach a pointer or an optical pin with the help of plastic material or masking tape, but here the pointer is already fixed. Then read and record the initial reading of the pointer on the meter. From the reading here, it reads 37.5. The S note should be recorded at the top of the table of results. After that, suspend a 50-gram mass at the end point of the spring. Then record the new reading of the pointer on the meter roll. The new reading is 39.2. Repeat the same procedure by adding masses of 100, 150, 200, 250, and 300 grams. Replace the 50-gram mass with a 100-gram mass and record the new reading of the pointer on the meter roll. The new reading is 40.0. Again, replace the 100-gram mass with 150-gram mass and record the new reading of the pointer on the meter roll. The new reading is 42.6 centimeters. Again, replace the 150-gram mass with two 100-gram mass. Then record the new reading on the meter roll. The new reading is 44.6. Replace the 200-gram mass with 250-gram mass, and again take the new reading of the pointer on the meter roll. The new reading is 46.4. Finally, replace the 250 grams with 300-gram mass and record the new reading on the meter roll. The reading is 48.2. After that, find the extension X by subtracting from the final end reading with the initial reading. So if I take 39.2 minus 37.5, the difference here is 1.7. 40 minus 37.5, it is 2.5. 42.6 minus 37.5. It is 5.1. 44.6 minus 37.5. It is 7.1. 46.4 minus 37.5. It is 8.9. 48.2 minus 37.5. It is 10.7. From the aim of the experiment, that is to find out the relationship between the extension and the load applied on the spring, we can see that as the load increased, the extension also increased. Now, draw a graph of load versus extension by using the collected data here from the table of results and drawing the graph of load versus extension. The nature of the graph is straight line starting from the origin, showing that as the load increased, also the extension increased. The relation is known as Hooke's law, which states that within elastic limit, the extension of a material or spring is directly proportional to the load applied. What challenges did you encounter on performing this experiment?
The densities of different liquids can be determined by using various ways. Depends on the nature of that liquid. The aim of this experiment is to determine the density of liquid which does not mix with water. Requirements: we have got water, motor oil, U-tube, retort stand, and the meter rule. The water will be used as a standard measure as far as it has got a density of 1 gram per cubic centimeter. Oil is the unknown density which you are going to determine. Then pour some liquid water inside the U-tube . Observe the level of the water inside the two limbs and found that they are of the same level. Then pour the oil inside one limb until it reaches some certain level. Observe the levels on the two limbs. We found that on that limb contain oil, it is a little bit higher compared to that of water. At this point, where the water and the oil are separated, the pressure on the two limbs are the same. So we can use that point to measure the height as the difference of that height by using the meter rule. Measure the height of the columns of this liquid, and that of water call it H1, and that of oil call it H2. Okay. The height of water column which is H1 is equal to 29 centimeters. Then we measure the height of oil, this is 31.5. From that equation, that pressure in liquid is given by density times acceleration due to gravity times height. Therefore, at the same level, the pressure in both limbs will be pressure 1 will be equals to pressure 2. Therefore, this will be given by that equation, rho G H1 is equal to rho 2 G H2. As far as the acceleration due to gravity is the same, therefore this will cancel, and therefore we may find that the pressure, the density of the liquid 2, that is oil, is given by density of the water times height of the water over that height of the oil. Substituting the values from this equation, we find that density of the oil will be given by 1 gram per cubic centimeter times that 29.0 centimeters over 31.5 centimeters, where this will be equals to 0.92 gram per cubic centimeter. From this particular experiment, we found that the density of the oil used is equal to 0.92 grams per cubic centimeter. Another way of determining the density of the liquid is by using an instrument called Hayes apparatus. Materials: water and cooking oil. This apparatus can be used to find the density of liquid which does not mix with water and liquids which mix into water. Place the beaker containing water in one limb of the Hayes apparatus and another one contain oil in another limb of that Hayes apparatus. Then By using the rubber tube with the clip, suck out the air inside the Hayes apparatus so that the liquid inside will rise. Then tight it. Observe the levels of water column and that of oil column. Then measure the height from one point where at that point the pressure will be the same. The pressure at 8 centimeters in both limbs are the same. Then we find the height of the water column is 29.5, while that height of oil column is 32. Now, when we find the difference of the two columns, that is